So today we will be covering the dot product and the cross product. We're going to start going over the dot product. So generally, we would be able to write the dot product as so. So our input is always going to be two vector quantities. And our output is going to end up being a scalar quantity. First though, we should give these vectors their components. We'll do x1, y1, and then we'll do a z1. And then for b, we'll do x2, y2, and z2. So this is actually a relatively simple algebra once you know the process. So we're basically going to be multiplying each of the components with their pair in the other vector. So, for example, we will be multiplying the x1 component in A times the x2 component in B, and we'll add those to the y1 component times the y2 component, and then the z1 component times the z2 component. So when we're done, it should look something like this. And that will end up being our result. And again, you can do this with any number of components. Doesn't necessarily have to be 3, even though 3 will be the most common we'll come across. So again, if you had other components, you could keep on going. So they could be anything. And we would be able to keep on writing these basically indefinitely to how many components you have. So this is known as the algebraic definition of our dot product. But we would also be able, there's actually a second definition that comes in handy. It is known as our geometric definition of the dot product. So again, our inputs are going to be the same. It'll be a vector A times a vector B. Well, necessarily. So it'll be a vector A times a vector B, and what that will be equivalent to, it will be equivalent to the magnitude of our vector A times the magnitude of our vector B. And this can be cosine of the smallest angle in between those two vectors. So this is useful for many reasons. First off, say if we are given vector A and vector B, we could always solve for this theta value for the angle between them. And the way we would be able to do that is we could combine our algebraic definition from earlier with this geometric definition and just do the arc cosine of this function. And remember from earlier that we have this equation over here for our algebraic definition. Just to save some room, I'm just going to write it as a dot b, but it will be equal to this up here. So essentially all we would have to do is divide these magnitudes over. So we would have a dot b, so this will be the cross product from up here again, the dot product, this algebraic version, over the magnitudes of vector A times the magnitude of vector B. And we are going to take the inverse cosine of this, and that will give us our theta value. So that's just an example as to why these two different definitions are very useful and how you can use them with one another to solve for something that you may not be given in the equation. So yeah, so again, very useful. And again, this value, this geometric definition, gives you a scalar quantity as well. In case you didn't know, and how to find the magnitudes of vector A and vector B, that's also a relatively simple process. So in order to find that, I'll give you the examples of these two. So it's pretty simple. We're just going to take the square root of each of these components squared. So by that, I mean we're going to take our x1 component, we'll square that, add our y1 component, we'll be squaring that, and then we will also be squaring our z1 component. And then this right here will be equivalent to the magnitude of vector A. And then for vector B, we'll do something again, same exact process. We'll have x2 squared. Sorry, it's me a little confusing because the subscripts are 2 as well here. But we will then have y2 squared plus z2 squared. And again, this will equal the magnitude of vector B. And again, that's going to be universal for any vector when you're given it in their components. And again, in case this is your first encounter with vectors in general, there are going to be two main ways you're going to see a vector written in its component form. So this right here is a good example of one way it may be written. Usually not with these underlines, though. We'll get rid of those. But that's going to be one way you could write it. But you could also write the components in this way as well. So again, say we have a vector A, we'll write it as x1i plus y1j plus z1k. So for each of these, as you can tell, they have these letters that follow, I, j, and k. These are going to be our coordinate unit vectors. So again, if we're looking at this as like a 3D space, we'll have a z coordinate, we'll have a y coordinate, and then we'll have our x coordinate. So basically, every single one of these, letters, so I, j, and k, they'll give you a direction in the x for I, the j is in the y, and then the k is going to be in the z. And every single one of these are only going to have a magnitude of 1. So essentially they allow you to just give a direction to the magnitudes that accompany them. So that would be our x1, our y1, and our z1, and then the I, j, and k just basically designate which way in our 3D coordinate system that those components are directed in. But again, you could also just write it as we had before, as with these brackets, and then we could just have like x1 again, y1, and then Z1 with these arrowed brackets around them. So either way, it doesn't usually matter unless you're told to write it a specific way, but they basically get the same message across no matter which way you do it. Yeah, so that's good for that. Right now, I think if you're just going for like a very basic understanding of the dot product, that should be more than enough. And I think for our second part, we'll be going over the cross product as well. So the cross product will be pretty similar to basically the setup is fairly similar for the geometric definition as dot product, but we'll first start with the algebraic definition for the cross product, and that's going to be a little bit different than what we saw for our dot product. So the most common notation for that will look something like this. So again, instead of a dot, as you may be able to tell by the name, we're going to use a X or like a cross symbol to designate that we're doing the cross product instead of the dot product. So we're going to use the same vector values that we had before in their components. So we'll say A is equal to x1, y1, and z1. And we will say that B is equal to x2, y2, and z2. All right, and perfect. So first we'll be going over the algebraic definition. And so essentially what we're going to do in this scenario is we're going to make a 3x3 matrix with each of these components. So for the two rows, you may be able to easily identify what we're going to be using here. We're just going to use each of the components of these vectors. So you may be asking how we're going to fill out the third row, but that'll come back into play with the different version I showed you earlier of how to write a vector with the I, j, and k unit vectors. So what we're going to do here, it's also very, very convenient because it helps you keep track of which row is which column is which. We're basically going to start the columns off with each of these coordinate unit vectors. So we're going to start with I, we'll go with j, then we'll end with k. And then under each of these, we will write the respective components that belong to each of those coordinate axes. So again, with I, as we said, just associate I with x. So all of the x components will be going underneath our I value. All the y will be going underneath our j value. All of our z will be going underneath our k value. So we will have x1 under I, x2 under I, then y1 under j, and then y2 under j. Then the same thing goes with our z values. And there we go. Okay, so now we have our matrix set up. Now we have to solve it. So this will be our general formula, I guess you could say, for solving these matrices with three components. But unlike the dot product, as I said, we could keep on going for how many ever components you had. With this one, especially if you're doing like a Calc 3 class or something similar to that, you will only be able to do this with three components in your A, with A and B for the algebraic definition of the cross product. So what we're going to want to do here is we're going to want to make each of these into basically 2x2 determinants and use those to get a vector value output. So again, that's another main difference between the cross product and the dot product, is that in the cross product, you input two vector functions, and your output is also a vector. So again, each of these are a vector, and your output will be a vector as well. So you may be asking how we're going to solve this. The easiest way I found to solve these matrices is basically to cover up each column. So if we want to solve for the x component, or the I, whatever you want to refer to it as, basically we will ignore everything in the underneath the I column, and we don't really need to worry about those two top unit coordinate vectors either. So we're only going to be focusing in this little 2x2 matrix down here with the y and z. So what we're going to do is we are going to do y1 times z2, y1 times z2, and then we're going to subtract z1 and y2 from that. And then that will be our I component. Now, the process to solve the remaining components of this vector are going to be fairly similar. Only thing is, we will now be looking at the other columns. So in order to do J, one quick note with J, there's always going to be a minus sign in front of it. And again, if it happens that your J component, you get a negative output for that 2x2 determinant, then you'll do the same thing as if you were just multiplying a negative by a negative, and it would become a positive. That's just how it's going to work for our J value, so just always remember to input the negative in front of it. And now we're going to write that out. So again, we're going to act like we're ignoring the J column. So we will have x1 times z2, and then z1 times x2. Because again, we're acting like the J column doesn't exist. So we will have our x1 and z2 minus our z1 and x2, and that will be our J value. Then it will alternate back to a positive, so we're going to be adding our k values in. And again, we'll just act like the k column doesn't exist, and we will be multiplying x1 times y2, and that's going to be minus y1 times x2. And that'll be k. Oh, can't forget to add the little toppers to each of those. Perfect. And then that'll be your general formula. And again, in terms of like introductory level dot and cross product information, for the cross product, you're usually only going to be able to do that with a vector. Well, vectors that only have 3 components. But going back to what we were talking about earlier, there is also a geometric definition. Of the cross product. So this one is going to be very, very similar to what we saw with our dot product. So again, we're going to have our magnitude of A times our magnitude of B. But this time, instead of cosine, you will have sine theta. So, this does come in handy quite a bit, especially if you're not necessarily given the components, but you're given the magnitudes. You would still technically be able to solve the cross product, but you'd be given the magnitude of the cross product values, and again, that is very, very convenient. And you can use that again to solve for the angle theta here, which again is going to be the smallest angle between the two vectors. And like I said earlier, you could technically convert this, we'll call this R vector, because again, this is a vector quantity. You could find the magnitude of this cross product by taking the square root of each of its components squared. And then again, just act like this x3 is this whole I component, this y3 is this j component, and this z3 is this k component. And then you can also solve that, set that equal to this, and then divide by the two magnitudes again and solve for the arcsine of that function to get the theta value. Alright, again, both of these are very useful tools, and especially for any physics class, again, vector calculus, and most engineering fields. These are basic concepts you'll need to know.